Hello, my name is Patrick Haley, and today I will be presenting my variable intake runner project for ME1311. Today we'll be going over the introduction, the problem, the solution, the code, the results, and the conclusion. First up, we have our introduction. We'll now introduce an intake system. An intake system consists of four main parts: a throttle body, a restrictor, a plenum, and runners. The throttle body is what allows air into the system when the pedal is pushed. It has a valve, which is this black bar right here, that gets activated based on how far the pedal is pushed. And then there is the restrictor, which is this tiny piece right here, which restricts airflow into the plenum, so that way, because of Bernoulli's principle and Bernoulli's equations. Then the plenum is where the air is temporarily stored in a vehicle, and the runners are what run the air from the plenum to the engine during the intake stroke. Important things to note about the system is that the air, when flowing, bounces back and forth from off of the top of the cylinder head back to the back of the plenum. And these bounces are really important, and we want to line them up with our intake stroke of each cylinder, so that way a bounce is going into the engine whilst the valve is opening. And this is dependent upon our RPM. Our problem is that our current intake our current intake runners are not at an optimal length. They are at an arbitrary length, and we need to find an optimal length. Why do bounces matter? Because if the bounce is going away from the engine when the valve, or when the air is flowing away from the engine when the valves open for the air to come into the cylinder, then it will be resisting airflow, and that's no good. We want the bounce going down to increase airflow, or not down, towards the engine whilst the valves are open, to have more air into the engine. Our goal is to find the optimal length of the intake runners, and we will be doing this by comparing data points. The solution, we have our MATLAB code as our current solution, and a dyno test. These are the equations used. We have our degrees the valve is open to, and using our RPM value, which is set from 4,000 to 14,000, we can get a degrees per second value, and from that degrees per second value, we can then divide our valve, the degree the valve is open to, by that, to get the amount of seconds the valve is open. And then from there we can get our pulse distance, and our pulse distance divided by our intake runner length gives us our number of bounces. And now we will do the code, or we will go over the code. Here's the first 14 lines of my code. It starts off with clearing the command window of all previous variables, and then clearing the command window of any code that was left behind and formatted in the short G format. Then the code will ask an input from the user for the intake runner length in inches. And then our constants are our RPM from 4,000 to 14,000, our Y degree, which is dependent upon our RPM, the Z seconds, which is dependent on our Y degree, and then our pulse distance, which is dependent on our Z seconds. And our bounces are equal to our pulse distance divided by our intake runner length, and then the bounces are rounded. And then we set up a while loop to determine the length of an array. And how we do this is we're checking for whole number integers in the bounces. So the Z and Z1 checks if it's a whole number or if the number of bounces is a whole number integer, and the test from A to A1 tests if it's an even integer. We do this by dividing the number by 2. And if it's not a whole number, then it is not even. And for every even integer, there is 1 added to the array, to the length of the array. And then we take the length of that array and make a new, or we take the length of our data from before and make an array of zeros called RPM boost. And from our RPM boost, we can then do the same test again for integers and even numbers, and instead of just making a counter, it records the data with the corresponding values at each for each spot in the counter, or for each spot in the array that was given by the counter. And then finally, for our final while loop, we set up another array of our RPM boost clean, which will average the numbers together and remove all zeros from the array. So the RPM boost, if our RPM boost is not equal to the next value in the RPM boost, then it will record the data and put it into the new RPM boost clean array. However, if it is equal to the next RPM boost number, then it will take those two numbers. So if the bounces are equal, I should say, if the bounces for the RPM boost are equal to each other, then it will take those RPMs and add them to an average calculator and keep repeating itself until the next number is not a different number of bounces. And then it'll take the numbers that we've gotten and average them together for the number of bounces, or average our RPMs for repeat number of bounces. And then finally, we remove all zeros from the bounce row and the RPM row. We do help seal and help floor to show the commands that weren't used during the year, during the semester, at least to my remembrance. And then we display our RPM boost clean, and we plot it and label our X as RPM and our Y as the number of bounces. The results. Here are the results first, we can see that the code asks for a runner length in inches, and I put 5 for my first, and it shows the seal and the floor command that I used earlier, and then it gives us the columns 1 through 16. So it takes an array from, at the beginning, the array was a size of 10,001, and it compresses it down to 16 values. And we can also see that our number of bounces indicate that the lower the number of bounces, the higher number of RPM, which is correct because when the RPM is higher, it gives less time for the air to bounce back and forth inside the runners. And here's the graph for the figure, or for our our runner length at 5. And then I repeated this process for 5.25 inches, and here's the graph for that. 5.5 inches, and here's the graph for that. 5.75 inches, and here's the graph for that. And 6 inches, and another graph for the 6 inches. And after doing that, we can then fill in this chart that we have with these nice placeholder numbers to then find the most optimal, and then we can dive deeper if we want to, and run the study again with a smaller interval. But first, we fill out what we can, which is our targeted RPM. Oh, I just realized my cursor's been on the screen. Our targeted impulse RPM at 20 bounces, at 30 bounces, and at 40 bounces. And then once we take the car and put it on the dyno machine that we have for the KS6C, then we can can get our max horsepower, our RPM at max horsepower, our max torque, and our RPM at max torque, and that those relations will show us which is most optimal between the bounces, the max torque, max horsepower, and the RPMs at those respected values. And as you can see, we have the data for the current runner length, 5.624 inches. And we just need to repeat this with an actual runner length of these sizes. In conclusion, we were expected to find the optimal length that best utilizes horsepower and torque. A successful test will show the greatest peak power curves at a given runner length. An inconclusive result will show less than 200 RPM difference or less than 5% shift in power curves between runner lengths. And a valid result will show that a specific length will generate the best balance between horsepower and RPM, which is what we're looking for. And this concludes my results because currently the car is not built and is going to be built by January. And then I will be able to continue this test and get the specific values I have. But this is the MATLAB portion of my test. Thank you for listening.